So this file, where is the file? No. So I'm going to create a new file with the DCA probabilistic. I'm going to call it DCA probabilistic for students. DCA probabilistic student. And what we are going to do here is I'm going to start with a Joshi equation. And let me show you a bit of on the GitHub what we have for this exercise. Actually, I can show you this one here. So what we're going to do here is we have a Joshi equation that we're going to use. So we're going to generate our own functions for Joshi. We're going to estimate some reserves using the initial rate from the Joshi equation. The Joshi equation, if some of you may remember it, as a way to forecast the inflow performance of horizontal wells. And it has some values like the permeability, horizontal permeability. You have the viscosity VO of the well, formation volume factor, the radius of influence of the well, the radius of the well itself, and KVKH ratio skin factor, and of course the length of the well. So I'm going to go over that. We're going to show you what are the results of a Joshi equation for different lengths, and at the end we'll show you some probabilistic performance or probabilistic forecasting with mixing the ARPS equation with the probabilistic Joshi performance as well. So for that, I'm going to do it exactly as the previous one. I'm going to do it from scratch. I'm going to copy all the stuff that we need for this exercise. I'm not going to write everything from scratch as the previous exercise, but we're going to use stats. That's probably the new thing that we will be using. And stats is a quite useful library. So if you Google for SciPy stats, there are quite a few other libraries, but the SciPy comes with the stats library where you can do quite a few things. So the thing that I like the most to use it for is to sample from whatever distribution you may want to sample, similar to Crystal Ball. So you have all these distributions here. And I'll show you in a bit. I'm going to show you only with a normal distribution how to use it. But the other thing that you can do with SciPy stats is if you actually have some data and you want to extract the theoretical distribution that fits into that data, you can also do a bit of a code to do that. I have some examples that probably later on, once we go over all the exercises that we have in the pipeline, I can show you those examples on how to sample from all these distributions, and also how to fit from a particular data. Let's say you have a permeability from different cores and you want to understand what is the distribution that you have on that permeability, if it's log normal most likely, so you can use the SciPy stats to return the distribution. So from the other books, I'm not going to write all the equations. I'm just going to copy and paste. But you have three equations mainly. You have the Joshi equation that returns an inflow performance of the well. So that J, it's actually an inflow performance. And you have the ARPS equation as the previous one. And the only additional one that we have here is the ARPS reserves or recovery, the ultimate recovery. So this returns the ultimate recovery given an abandonment rate for the well. So let's start defining some initial values, and I'm going to do it probably one by one. Let's say we have the first value. It's KH. and KH is equal to 20. The horizontal, I believe that we can do something like this to do it in a more linear way. I believe so. No. How is it? I forgot how to do it like that. So the horizontal, let's say the reservoir thickness, it's 100 feet. The formation volume factor of the oil, it's 1.1. We have a mu of oil viscosity of 0.9. We have a KV/KH ratio, the original value estimated of 0.1. We have the radius of influence of the well of 600 feet, a skin factor of, let's put it as 1, no simulation on the well, and I'm going to put it this explicitly because it plays a lot of a bigger role later on. It's a well length of the well length is 5,000 feet. We have a delta pressure of 500 psi and the welder radius as 0.33 feet. And we can call Joshi, and I'm going to call it as a productivity index of a well. It's let's call it productivity index. Well, I like to use lowercase because it's more the way in which people programs in Python, especially on variables. So if you put upper cases, it's usually you're writing more functions or classes. So I'm going to stick to lower cases, and I'm going to use underscore for the time being as well under the variable. So I'm going to have J Joshi. So I'm going to call it J Joshi. J Joshi, and I'm going to pass all these values. I think the only difference is that we call the L, we call it well length. So if I run that, I have a productivity index of that magnitude. If I want to have a rate, you will remember that your rate is equal to your productivity index times your DP. So if I want to return the rate, that's the rate of a well for those given values. So let's do something more fancy, and I want to calculate the rate for different well lengths. Let's say I want to understand what is a well length that I would like to drill my well. So I'm going to put wells length. So several wells here. I'm going to use NumPy linspace. If you remember NumPy linspace, I can do things like I have a well I want to try from wells from 3,000 up to 10,000 feet, and I want to try 9 wells. So if I print that well's length, notice the difference is well's length. These are the tries that I'm going to execute. So now I'm going to have a series of rates, and I can simply call the Joshi equation with all the values that we had before. And instead of well length, I'm going to type well lengths. So if I do that, notice that well's length. Well's length. well length spelling. There you go. So this rate seems a bit odd, a bit low, and of course I'm missing the DP in the wells. There you go. And if I want to plot, let me do a quick plot, and I'm going to do rate versus the wells length. Let me do it properly. Length. Well length. Oh my goodness, what's happening here? The shape is 109. Okay, again, recording my errors. This is rates. Right, so great, that's fine. The equation is sort of useful, but not super useful because this is almost like, well, if I add length, I would always have an infinite amount of rate. It doesn't matter how long is the well, but we know that, of course, there is friction and acceleration ongoing on the well bore, and with the friction losses, the well performance would be more. Will have a higher decline. Will have a decline. Actually, it should be the other way around. Yeah. So we should have lower rates, which at some point, as we start to increase the well length. But that's fine. We can use it. We can still use the equation. Now let's do something a bit more interesting, and I'm going to do a bit of a sampling. And for that, I'm going to do a sampling with, let's start with 100 values, just to show you how good is the performance of Python at 100, 1,000, and 10,000. So 100 values, and I'm going to have a variable here, which is my beaming, which is the size of my histograms, that I'm going to do some histograms plots later on. So let me run these two, and this is, if I want to add something here, this is a start of probabilistic input. And of course, this is a markdown. Probabilistic, Right. So now, one thing that I'm going to do is to use SciPy stats to do a sampling for my horizontal reservoir thickness. Let's say there is a bit of uncertainty on the reservoir thickness, and the reservoir thickness, if I use stats, I can use, as you know, all these different distributions. I'm going to use normal distribution, and I'm going to do a random value sampling. The size of my random value sampling is going to be equal to a sampling variable, so that's only 100 values. And I want to have a mean value of 50 feet of thickness with a standard deviation of 10 feet. So if I show you what I have as an H, let's do a plot. So I have 100 values where my mean is 50 and standard deviation of 10. And I can do, let me do a plot of the histogram. So I can do blt.histogram, and let's call it histogram of H. Okay, it doesn't look that nice, but there we go. That's the first histogram that we're producing. And just to make sure that I can edit the binning of the histogram, I'm going to say binnings equal to binning. And I'm going to leave the default color of that you see there, right? So that's my first histogram, and I'm taking values from around 30. I'm taking one value, and 30 plus between 30 and 40. I'm taking about 8 plus 5, 13 values. So you can see how many sample values I'm taking of a total of 100. So if I do, let's do 1,000. So there we go. So 1,000, you see how the scale is changing because I'm sampling, of course, much more values. And I can also play a bit with the binning and make the plot a bit more tidy. Well, not tidy, but I have more bars in the histogram, which I particularly like a bit better. Right. So there we have. Let me clear this output here for the horizontal for the reservoir thickness. And let's do the same for the KVKH, and let's do the same for the KH. And actually, yes, KH, KVKH, and I'm going to do for the KVKH, I'm going to have a mean value of 0.15, and the, can you listen to me? Hello, can you listen to me? Okay.
Yeah, we can hear you.
Okay, someone was complaining about the audio. So the scale is 0.05, which is the standard deviation of the KH. Sorry, of the it should be KVKH. KVKH. And for the KH, I'm going to use roughly 20 and 3, right? So I'm going to do a bit of an arrangement of the plots, and I'm going to create a figure, a subplot. I'm going to create four or at least 4 subplots. So for the H, I'm going to make subplot 2, 2, and I'm going to make, so this is going to create four plots, 2 at the top, 2 at the bottom, and I'm going to put my histogram of the H at the top, and I'm going to do something similar for this. Now this is going to be at the top right, and this is for KVKH, and this is going to be bottom left, plot number 3, and this is going to be KH, and let's run it and see what happens there. Okay, it's a bit tiny. I don't particularly like it, And one thing that we can do is, as we did previously, I can change the figure size. So let's say prt.figure and user fig size equals to 15 times 6. Let's see if that works. I don't know why these arrays are coming in there. Okay, that works all right. That works okay. I think I can make it a bit thicker. There we go. I'm going to change the bin to 30. Okay. Now we have sample H, KVKH, and KH. What I'm going to do now is run Joshi with those values. So now I'm going to have rates similar to what we did here. And I'm going to fix the well length. It's going to take this one here, well length. And obviously the H is going to be overwritten. KV, KH, and KH are going to be overwritten. So we'll have some new rates. Oh, okay. I think we have to convert this to NumPy arrays. We have to convert this H to an NP array in order for it to actually work. This is what I was showing you the other day. The other day I was showing you a function that worked with a list, but usually you have to convert it to an NumPy array if you don't want to make it a for loop. Okay, hopefully that will work. No. What's going on here? Oh, sorry. Okay, there we go. So we have our rates. The only thing that I'm going to do to make it a bit more to plot the outcome of a rate, instead of plotting it as a histogram, I'm going to plot it as a cumulative distribution function. And for that, I'm going to copy the values. I'm going to copy some of the values, some couple of lines that I have here. Actually, let me do it like this. So we can do values and base equals to np dot histogram of rates, bins equal to bin, and cumulative is equal to np, the cumulative sum of these values. And I think that should be it. Let's see if this works. And I'm going to plot it in the fourth plot. not working here. Just a second, let me see. Range parameter must be finite. What is not finite? Rates. Okay. I'm not quite sure what's going on here. Oh, I need the cumulative maximum. Okay. No, range parameters must be finite. I'm not quite sure what's going on here. So the idea is to produce a cumulative distribution function plot that shows for the rate. So what we're trying to do is estimate on one axis, it's the 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 actual distribution, the distribution function that goes from 0 to 1. And on the other axis, we should have the values. I'm not quite sure what's why this is not printing the right numbers. Let me see. Range parameter. I'm not quite sure what's going on here. In fact, range parameter must be finite. Histogram A beams range. Let's see what's going on. So this is one of the best sources to debug, to understand errors. So Stack Overflow. So whenever you look for an error, you most likely will fall into Stack Overflow. And if you have a question, 99% of the cases you're probably sure that you will find the answer in Stack Overflow. Okay. Oh, I see what's going on. So you see some of these values are going under 0. So when I run the distribution for I think in this case is what is this? The KVKH, I'm going below 0. So I have two options. Either I fix the distribution by changing the values, or I simply truncate the distribution. So I can simply say KV, KH, if KV, KH, it's lower or equal to 0, then I'm going to fix it to 0.001. Okay, let's see if that works. There we go. So now we have a cumulative distribution function. And to add a couple of additional items to the plot, I'm going to add the P10, P50, and P90 of a plot. So for that, I'm going to say P10 is equal to NP, so numpy dot percentile, and I'm going to pass the rates values, and I want the percentile 90. Sorry, I want the 90 in this case. If I want to have the inverted, because I'm plotted the inverted cumulative distribution function, so I need to put it the other way around. So if I would plot it the direct one, you will put 10, 10, 90, 90, and 50, 50. Okay, so let's do that. And I can use the annotate, and I'm going to just copy and paste here. So annotate, and I can more or less indicate what I want to do the annotation. If I run it again, there we go, P90, P50, and P10. And these are my outcome of the Joshi equation. So we have done only Joshi so far. And the last bit of the exercise is to do the actual decline curve analysis with the Joshi value. So let's see if we can do it before we finish. So we have to do DCA, probabilistic, and this is actually start probabilistic input with Joshi's rates. And this is the DCA, this is a full DCA probabilistic. Okay. So for this, I'm going to generate an array of time from using the line space from 1 day up to I don't know, 10 years. 10 years is more or less that. And I want only 200 values. Okay. And my initial rates, or my initial rates for ARPs are going to be the rates that I calculated with Joshi. In fact, let's put rates Joshi, and I'm going to call it here rates Joshi just to make sure that we're clear on what we're using. Okay, and for the remaining reserves, let's say we're going to shot the well when the production falls below 200 barrels per day, because this is a super well, and let's be realistic, let's put 100 barrels per day. We're going to fix the beta factor for this exercise as a hyperbolic decline with a coefficient of 0.5, and the decline rate, let's do our decline rates, and this is where we're going to do stats again with the normalized random value sampler, and we will use the size, same sampling size. We will use the mean coefficient of 0.00 0.01, which remember that we're talking about daily declines in this case, and the scale, it's the standard deviation of 0.221. Okay, and just because we already have that problem, just let's make sure that if the decline rates are below 0 by any chance, let's make sure that they are super low. So we know also that the EUR of a well is equal to the ARPS reserves, the equation that we already defined above. So we have initial rate, refactor, and abandonment. Let's see if we can. So initial rate is initial rates, beta factor, decline rates, and abandonment, I put as abandonment rate. So let's see if I have EUR. There we go. So we have some millions of barrels of cumulative production by that well. We have several values that we are forecasting here. Right. So let's do the same trick of the percentiles. P10, P50, P90 for the ultimate recovery. And the last thing that we're going to do, and I'm not going to go to the details because I think we have done quite a bit on this one. It's a plot the results. So for that, I'm going to, because we are changing the, let's call it, we are changing, I think we're changing here the decline rates, isn't it? I think I'm changing the decline rates. So this should be actual decline rates. And this is a decline rate histogram. And we're plotting EUR, and I think this should be fine. Let's see if that works. Yes. So we have the decline rates changes that we put. We have a P90 as the lowest that we can produce is 11. But if you see here, we have E7. So that's it's actually 110 million. Wow, that's sounds like quite unrealistic well to start with. But there you go. This is a simple example, probably because of the prediction. I don't know. I think the prediction should be all right. I don't know if there is something right with the strange with the scale that I'm trying, but there you go. That's the example with the probabilistic, and as you can see, we are using the initial rates that we are using are the rates of the Joshi, so the actual rates that you get out of the whole sampling of or the Monte Carlo that we did above, and the actual ultimate recovery is a combination of the initial rates of the wells and also the uncertainty on the decline rate of a well, and this is a range of a potential ultimate recovery of the well. Of course, you can start to change things like the abandonment rate. Let's say if we may abandon the well at 250 because the well, let's say, may have a problem at a lower rates and might not be able to flow. And if there is a pump failure or something, it's very difficult to save the well. So you can see how the cumulative production of the well actually it's being reduced. So likewise, you can also review these rates that might be a bit high, and probably the length of a well, it's 5,000 doesn't look like unreasonable well length. And let's say we have the reservoir thickness, it's lower. Let's say it's 30 with a lower uncertainty on the standard deviation. And I'm going to increase for the sort of playing with the data, the binning, and also increase the sampling size to 10,000. So look at this. I'm running already 10,000 cases. It's taking a bit of time, but it doesn't go beyond 3 seconds. So it's quite quick and a very smooth curve here and a very smooth histogram. So the sampling size obviously improved the histogram. And Ray didn't look like it was going down, not so much with that given H. But there you go. This is the full exercise of a probabilistic that I wanted to cover. So I think that's for today. I have some time to answer questions, but I think that's it for the session today. So any questions so far? Anything that you want me to go through? Just let me know or write in the chat, please.